Hi, good morning, Kelvin. Okay. So, Kelvin, have you come to campus? Have you come to campus? Because I know Noel had come to campus previously, but have you ever come to campus? Not yet. Nah. Okay, so I think this week is already in week 13, if I'm not mistaken. Yeah. So this week is already in week 13. Next week is in week 14. So I think you have to come to campus just to make sure that you will not lose letter during the exam face to face. Both of you lah. If you come to campus, please identify which is block B, which is block A, which is block C, so that later for your exam you won't be lost lah. Okay, Kelvin and Noel, and also practice to write using your hand. Practice your handwritten so that it can be read because we are now really like we write long time ago. Usually we are now typing. So yeah, of course, sometimes even me also, my hand already keras to write, but I still can read my handwritten lah, handwriting. Okay, so make sure you practice your handwriting so that it can be read. Nanti if it cannot be read, then no marks because don't know what because the marker don't know what to write. Okay, it's like jangan become the doctor punya tulisan. Okay, Kelvin and Noel.
Okay.
Okay. So let's okay. Let me share my screen. Okay, so last week, what we have learned last week is about hashing. Can see my screen clearly.
Oh yeah.
Okay, so what we have learned last week is hashing. So what is hashing? This is just a recap lah. So what is hashing? It is the technique to determine the index or location of a storage uh, of an item in a data structure without doing any searching. Because why? The index of that item is already stored in that key itself. So we can directly just go to that item based on the key. Okay, because in that key it is already containing the in the locations of that item. So that is hashing. So what is hash function? Hash function is the maps. It is the function that maps the search key of an entity into a location that contains the item. So the process of hash functions is to map the key and then the location in the memory, okay, where we put that key or that item in our memory. So the process of mapping that key to the location in the memory, which we call as hash functions. So hash function, there are two steps that we have learned previously last week, which is the first step, we need to find the hash code first of whatever object or primitive type object. So before we can go to the finding the index of that object or that um, item types, we need to get its hash code. So we have learned two types of how to create hash code or how to get hash code for primitive type and then for class instance. Last week we have learned. So this is the example of how we can get the hash code for a class instance. Okay, so for example here we have the class which is the telephone number last time that we have learned. Okay, so how the hash code obtained are by just getting the last four number in the data in the phone number. Okay, so and then we can already get the hash code. But for the primitive type, which is for example the byte, short, integer, all of these, sometimes we can just get the number of itself, mean the value of that integer itself to become the hash code. But for the string, yeah, I forgot to put here. There are another hash code where that we have learned previously, which is how to get the hash code for string. So we have learned about two types last time, which is first we may assign number 1 until 52 to each of the string. Okay, so from the capital letter until the small letter. Okay, so that's why we assign number 1 until 52. After that, another way of giving the hash code to a string is we get the ASCII code for that string so that we can get the hash code. So that is what we have learned last week. So after we get hash code, we need to compress the hash code into range of indices for the hash table. So after we get the hash code, then we need to compress it. So we have learned about how to compress it, which is using modular lah. Okay, so there are various ways, but the one that we have learned is using modular. So this way is the second step of hash functions. So remember hash functions, we have two hash functions, which two steps of hash function. First, determine the hash code, and then second is compress the hash code into so that it can become indexed in a hash table. Okay, so we also have learned about the feature of good hash functions. So because in the hash code, when you determine a hash code for any class instance, it is depending on you, on how you create the hash code for that class instance. For example, here, the experts decided to just get the last four number of that telephone number to become the hash code. And then, so, so your hash code should be, okay, so your hash code also will determine either your hash functions is a good hash function or not. So what is a good hash function is the hash functions that can minimize collisions. Okay, so we have learned about collisions, and and then a good hash functions also must distribute the entry uniformly throughout all of the hash table, meaning it cannot be berat sebelah. The entries must be distributed. They are in the left, they are in the right, they are in the middle. So it must be stable lah. And then after that, your hash function must be fast to compute. So yeah, so these are the characteristic of a good hash function. So last week also we have learned about this. But some of it here we will learn after this. So last week we also have learned about collision. So what is collision? Collision is when there are more than one item that is mapped to the same array location. So that is collisions. So in order to resolve collisions, this collision must be resolved. If not, then our system will have error lah, because each of that entry must be allocated to index. So if we cannot, so that's why we need to fix any collisions, because yeah, like I said just now lah, if we cannot resolve the collisions, then there will be error, because there are an entry in our data table or in our hash table that didn't have index. So in order to resolve collisions, there are two ways, which is first is open addressing, and then second is separate chaining. So this open addressing also known as this open addressing is actually the where the scheme locates the alternate location within the hash table. So for example, if that index already occupied, it needs to find another location inside the hash table. So that is open addressing, meaning it needs to find alternative location for that entries. But for the separate chaining, it is known as close addressing, because there are no need of you to find another or an alternative location for an entry. So why we don't need to find another alternative of um, alternative location for your entries? We will learn that later in the separate chaining. So last week we have learned three types of open addressing, where all of this type is um, to find all of this, where this technique is to find the alternative location of an entry that doesn't have index locations, because if the index locations calculated for it is already occupied, then it needs to find another location. So these are the three ways of finding another location. Okay, so linear probing we already learned last week. Quadratic probing, if I'm not mistaken, we haven't learned. And then also double hashing we haven't learned. Okay, so for this week, we will continue to this quadratic probing and double hashing. And also we will know about this rehashing and this separate chaining. Okay, so far clear of what we have learned previously?
Okay.
Okay. So I can share this link with you both. I share this. This jemput kan weird though. If we zoom it in kan, the what? If we zoom it in, the items in this blank space, in this white space, will become bigger. Yeah, and then when we zoom it out, then the UI becomes bigger, but the icon um at the in the tepi-tepi ni kan all become smaller. That's why it is like I think ni. Okay, so if I want to make this bigger, then I will need to zoom out. Okay, so I already share with you all, with both of you. So now we proceed to do quadratic probing and double hashing. So this is another technique how to find the alternative index location for an entry. Okay, so quadratic probing and double hashing. Okay, so we proceed with the quadratic. Okay, so quadratic probing is one of the technique under open addressing. Okay, so the difference between the quadratic and the linear probing previously is this one. Okay, so because of the linear probing previously, it can lead to the primary clustering. So remember, primary clustering is where the entries is not, it can become in one group only at the some part of the hash table. So it is not distributed evenly. So that is a primary clustering. So because of the linear probing will lead to the primary clustering. So that's why quadratic probing is invented. Okay, so the difference between the linear probing and the quadratic probing is on how it find the location. So if previously in the linear probing, if you both can see here, the location, it only will find the next location that is empty. So then it will max all of the, for example, if we fill in the left hash table first, and then all of the entries will be berkumpul at the left side. So that's why that is what happened in linear probing. So that's why there's primary clustering happen. So in quadratic probing, so instead of we are looking at the just next index for the alternative, um, I mean, instead of we are looking at the closest index, closest empty index, sorry, not empty, available, closest available index, we are using this application to find next available index so that the next entries, it won't be clustered in only one part. It can be evenly distributed lah. So it's like here lah. If previously k plus 1, k plus 2, and k plus 3, and then up until k plus n. Thus, if we make it like this, k plus 2, 2, meaning 2 to the power of 2 is 4, if I'm not mistaken. Okay, yeah, 2 to the 4. So meaning if the first location is at this location, k plus 1, let's say 0, and then the next location will be at the location 4. And then after that, the next entries will be keyed in at the location 3 to the power of, sorry, 3 to the power of 2. So the next location to be will be located or will be placed at location 9. Okay, so it makes the entries distributed evenly. So it will be continue lah, and then next will be k plus 4 to the power of 2, and then k plus n to the power of 2 lah. Okay, so that is quadratic because we use quadratic function here. So but there are a problem with this quadratic probing too. Okay, so we see later lah what is the problem. Okay, so the good of this quadratic probing is it can separate the cells widely. Okay, and then it will guarantee the successful add operation. But the add operations will be successful if the hash table is at most half full and the table size is a prime number. So this quadratic probing only can be successful to add to operate its add operations if these conditions are met, which is the hash table must be at most half full, meaning it cannot be full. It cannot be even over half. Okay, so it must be, the hash table must be at most half full. Okay, so paling penuh pun is half of that hash table. And then the table size must be in a prime number. Baru the add operation will be success if we are using quadratic probing. So these are the illustrations of the quadratic probing. So like for this illustrations, let's say your first entry is at K location, and then your next location is K plus 1. And then because K plus 2 to the power of 2 is 4, then the next location is 4 location after the K. For example, here kan, this is 4, meaning 1, 2, 3, 4. The fourth location after the first location of K. And then here is 9. So we need to calculate we need to calculate 9 times after the first location K here. So the example here, because this is K to the power of 2 is 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So the next entry will be here. And then 4 to the 4 to the power of 2 is 16, if I'm not mistaken. So we calculate that. From here, we calculate the next location from K. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10, 11, 12, 13, 14, 15, 16. Okay. So understand about quadratic probing, how it choose the next alternative index, the next alternative locations for an entry.
Yeah.
Perfect.
Yeah.
Okay. So the advantage of this quadratic probing is it eliminates the primary clustering because it can distribute the entries evenly. But the disadvantage of quadratic probing is it needs more effort to compute the indices for probe sequence than does linear probing. So because linear probing is just a simple calculation, so the quadratic probing has a little bit hard equations or formula. So it takes more effort lah to compute the quadratic probing compared to the linear probing. So entries that collide with an existing table entry use the same probe sequence, thereby increase its length. So it might lead to the secondary clustering. Okay, so but this secondary clustering is not a really serious problem, but it can increase the search time. So that are the disadvantage of quadratic probing. So another alternative besides the linear probing and quadratic probing is double hashing. So that means we apply we apply two hash functions when you allocating the entry to a hash table. Okay, so for example, this is your first key, the first hash function. So this hash, so and then you apply another hash functions to that entry. So the method is first it's search the hash table starting from the location that the first hash functions determine, and then if a collision occur, it consider every end location from the original hash index where n is determined from a second hash function. Okay, so if you read this, of course, you will need a little bit long processing time to process it in your brain, but later, if we see the example, we can understand more. Okay, so um, this open addressing with double hashing technique, it can resolve collisions by examining the locations. So, which location? It can resolve the collisions by examining the location at the original hash index, and then after that, it plus an increment that is determined by the second functions. Okay, so the second hash functions, it must be different from the first hash functions. And then the second hash function also depends on the search key, and it will return non-zero value. Okay, so we see the example later. So this double hashing advantage is it can reach every locations in the hash table. In the hash table, if table size is prime, and then it can avoid the weakness of linear probing and the quadratic probing, which is the primary and secondary clustering. So how? So this is how, by using the example lah. Okay, let's say we have table size is 7 and then the search key is 16. Okay, so first hash key, first hash functions, we apply because key modular with the size of the table, right? Okay, so here 16 because we want to search of 16. And then so 16 modular 7, the number is 2 lah. So the location must be in here, index 2. And then we apply the second hash function. So we key in 16 here, and then so we can get its value. Then the location for the second hash function is at 4, meaning we calculate 4 times from the 2. Okay, so if first hash function locating this location, so we need the next hash functions, we calculate 4 times from here. 1, 2, 3, 4. So that's why the next hash functions will be located at here, 6. Okay, so after that, okay, so after that, the next location is we calculate 4 times. So 6, we end with 6 just now, and then we start from 6. I mean, because we calculate 4 times, I increase 4 times after the 6, meaning 0, 1, 2, sorry, 1, 2, 3, 4. So that's why the next location is at location 3. If that location is available, if it has value in 3 here, then the next location will be 4 lah. Okay, so understand here. First, we need, I will repeat again. First, we compute the first hash function. So we know that we want to put the 16 at location 2. And then after that, we apply second hash functions. So we know that it must be increased by 4. So that's why the next entry, it will be put at the, after the 4 times. I mean, yeah, 4 times from the first location. 1, 2, 3, 4. So the next entry is 6. And then after that, there are no more entry after 6 years. So the next entry, we need to calculate from the zero lah. It going back to zero because there are no more number after 6, no more room after 6. So we calculate 4 times. So 1, 2, 3, 4. So the next, the third entry will be in the location here. Understand? Kelvin and Noel?
Oh yeah.
Kelvin?
Yeah.
Exercise. The following keys are to be hashed into a hash table of size 11. Okay, so these are the key lah, 1, 2, 3, 4, 5, 6, 7. Okay, but the table size is 11. So given the primary hash function is this one, T modulo 11. So, and that collisions are resolved by double hashing with the secondary hash function, which is this one. Okay. So, so how you should solve this type of problem is, first you do this table and then we apply, we compute each of that hash function. Okay, so after that, baru we arrange this value in a table. For example, this one. So what you need to do is, you need to draw a hash table that containing 11 locations, and then you sort this key to that hash table. Okay? Okay. So I think we need to use our Jamboard. So the page number 3, Noel, and page number 4, Kelvin. So based on, we already compute both hash function. Then you have hash table size of 11, meaning your hash table must have 11 locations, and then you and Noel and Kelvin. Okay, so Noel in the page 3, Kelvin in the page 4. I will give time up until 9:45, 10 minutes. Or until you both finish lah. Okay, Kelvin and Noel, clear about the instruction?
Yeah.
Okay. Sorry, I unshare my screen just now. Okay, so based on this value of these hash functions, no need to compute again lah. It will take time. So after here is it is already computed, then you just based on this arrange all of these key. Hmm. So, So if it is hard to draw in Jamboard, can just write on a paper and then you take picture and then up paste it in Jamboard lah. Because I saw like see Calvin having problem to draw the table
Yeah.
kan? So which where is easier for you lah? Maybe you can just draw on paper and then take a picture and then put it in apa. Or you can just WhatsApp me lah the what the screenshot. Not screenshot lah, the picture of your drawing. Because Jamboard also is not, it is also limited lah. Or maybe you draw it using pen and then copy paste it in here also can lah.
Do I have to do for every key? Miss, do I have to do for every key?
Yeah. There are 7 key, right? So there are 7 key and then you need to place it in a hash table of size 11. Secondary clustering. Actually, it is like the primary clustering, but secondary clustering it is produced by the quadratic probing. So imagine in your hash table, by using the quadratic probing, you already distribute them evenly, each of the entries. And then, but as the entries become bigger, the size of uh, as the entries become bigger, each of that part of that evenly distributed entries on that hash table also can become a cluster. So maybe there are a cluster from the left, there are also cluster from the right, and then there are also cluster from the middle. So even though they are evenly distributed, but there are some part that is still empty, and then there are some part is become cluster. Okay, so that will make, like in our slides say, that it is not a really big problem, but it can make the searching become longer, because if you need to add something right in the hash table, you need to search, or you need to go through all of that cluster. That means if it is a cluster in one place, then you need to check one by one, and then you still cannot key in the new entry because it is a cluster. So it will makes you the searching of available entry can become more time consuming lah. Okay, Noel? Okay, so we see. Oh, okay, finish already, see Kelvin, right?
No, I don't think so.
Haven't kan eh?
I think I haven't.
Okay. Eh, so tell me if you finish, Kelvin. You only need to consider the 7 key. There are no 1, there are no 4, there are no 8, only the key here. 11, 52, 32, 28, 85, 90, and 61. So you need to place this key from your location 0 until 10.
I think done. I think. Yes, I done. Okay.
I muted my mic. Okay, so we check the answer. Let's see. So this is your hash table. There are 11 locations here. So we need to place that number in this location, that key. So let's see who are correct. Okay, so Noel, not incorrect. Kelvin also incorrect. So maybe I think I understand your confusion here. So in this exercise, actually for the double hashing, only if we find a collision, then baru we need to consider the number of the, the location that is provided by the second location, by the second hashing.
I add collision on everything.
Itulah. That is the confusion here because what we have learned previously in the previous example, there are no number, right? There are no number. So it is not really clear lah, the example previously. So what we did first is, first we arrange this first. Since here, we just focus on the first hash function first. Okay, so it says that 11 is in 0. So we put 11 lah, no problem. And then 52 is at location at. So 52 here. And then 32 is at location 10. So we put the 32 here. And then after that, 28 is at location 6. Okay, no problem. But at 35, because there are collisions here, they are at. So a collision happening here. So that's why baru we take the value of the second hash function. So we calculate 5 times after location at. So imagine here is the 52 for the at, because it is already has value, has entry. Then we calculate 5 times. So 1, 2, 3, 4, 5. So location 5 is location 2 is empty. So that's why we can put empty 5 here. And then after that, we proceed to the 90. This key 90. So it is set in location 2. So location 2 already has entry. So that's why we check the value of the second hash function, which is also 5. So we calculate 5 times after location number 2. So 1, 2, 3, 4, 5. So location 7 is empty. So that's why we can put 90 here. So we proceed, last is 61. So it says that it is in location 6. So because location 6 has entry, then we check its second hash function. So which is 4. So we calculate 4 from location 6. So 1, 2, 3, 4. But 4 here already has entry. So we calculate 4 times from this location. Okay, so that's why 1, 2, 3, 4. So that's why 61 here, because because 61 is empty. Location 3 is empty. So it is after the second. There are double probing in there. Okay, so clear tak, Kelvin and Noel?
Yeah, yeah.
Oh, yeah.
Ah. So remember, only if there are a collision, then baru you need to check the value from the second hash function. Okay, so we take 5 minutes breakfast lah, not breakfast lah, breakfast. But if you want to take your breakfast, also can. I cannot lah. Okay, so we meet again at 5 minutes. Okay, so we continue. Are you both here, Noel and Kelvin?
Oh, yeah.
Yeah, here.
Okay. Actually, I'm freezing then. I'm in discussion room. Okay, we proceed. Okay, so we have already covered the three technique in open addressing, which is linear probing, quadratic probing, and double hashing. Okay, so, but by using these three technique, there are a problem. What is the problem? Yeah, so the problem is because of using those three um, technique, it can cause every location in the hash table um, to reference either current entry, which is in the occupied state, or a former entry, which is in the available state. So remember in our previous slide, a null status is needed for open addressing. Okay, so a hash table might have no location that contain null. Okay, so remember previously there are three sets of location, which is occupied, available, and null. So the one that can receive any entry is available, but null, it won't receive any it won't receive um, entry because it will be used for the search. So if this happen, okay, so because of this addition and removal, then in your hash table there might be a location, there might be no null location. Okay, so if this happen, the approach to searching a probe sequence will not work because if you remember previously in our page 47, it says that the searching will stop searching if they find a null location. So, but if in that hash table there are no null locations, then it can become a problem because um, it can be a problem because every unsuccessful search can end only after considering every location in the hash table, meaning it will continue searching but until it found null locations. But if null location is not exist, then it will be a problem. So how to solve that problem? Able to real. Okay, so remember here. So, like I said previously, these three technique can create no null location. So, if there are no null locations, the searching won't stop until each location are searched. So, it will be a problem. Like it will continue searching. So, how to solve this problem is by rehashing. Okay, so this separate chaining actually it won't um, it is not specifically to solve the problem of this because this problem will be solved by this technique. But separate chaining we will learn later. But this separate chaining will be better than this open addressing. Okay, but we will learn that later. So now we focus on the rehashing, how this rehashing can fix this no null location. So we proceed to rehashing. So This rehashing will expand the hash table to a size that is both prime and at least double its current size. So the hash functions depends on the size of the table. Yeah, so we know that the hash functions will depends on the size of table because we see that previously the hash functions is like key modular table size, right? So that is what it means. Okay, so this cannot copy element from the old array but put them into the same position in the new array. So we need to apply the revised hash functions with the new table size to each entry to determine its proper position in new table. However, doing so can lead to collisions. Thus, to ensure that collisions are resolved, use the method add to add the existing entries to the new larger hash table. Okay, so this theory is memang a little bit hard to understand. And then in our slide also, there are no more explanation, only this slide. But I found a good video explaining the rehash. But this video is 7 minutes video. So, but this video is 7 minutes video. So I want wasting our time because the time is consumed by the speaker writing on the on the paper. So uh, we will learn about load factor later in our slide, but for now I will give the example of rehashing here. So if okay, wait,
Number of buckets.
Oh, the background very loud.
Modify.
Oh, cannot hear the video.
In this video, we will take a look at load factor and
So
rehashing.
you watch that
So let's
video,
first take a
but
look
start
at what load
from
factor means.
minutes 2:41.
Suppose the hash function was erstwhile something mod n. We change to
Okay?
Okay.
suppose it was x mod n. We change this x mod n to x mod n dash. That's the modification we have to make in the hash function. So there are two main steps. We have to increase the number of buckets to n dash. Then we have to modify the hash function to x mod n dash. After that, the third step is going to be apply the changed hash function. Let's call that h dash of x. So this is the modified hash function. Apply this to the existing elements. So we have to apply the modified hash function to the existing elements. After that, we can say we have gotten an enlarged hash table, and in that case the load factor will be definitely less than 1. Now, what is the condition for n dash? We say that we need to increase the buckets to a size n dash. So what must the value of n dash be? So what is n dash? N dash is going to be the closest prime number to the value 2 into n. So we are going to double our previous value and then take the prime number which is close to that. So we are going to more or less double the size of our bucket array. So let's take an example.
The bucket
Let me say that
the speaker mentioned here is actually referring to the size of the table. If she say bucket, this bucket, meaning it is the size of the table, hash table.
my hash function is going to be x mod 3. Let's say the keys I have are, say it is 6, 7, 8. So now my bucket array is going to be the hash value of 6 mod 3 is equal to 0, so I will add 6 here. Hash value of 7 mod 3 is equal to 1, I will add 7 here. Hash value of 8 mod 3 is equal to 2, I will add 8 here. Now the number of entries is equal to 3, capital N is equal to 3, therefore lambda is equal to 1. Now lambda is no longer less than 1, so it is time to rehash. So what should my n dash be? N dash should be double of the n and the closest prime to that. So now I get 2n as 6. Now I have a choice between the prime number 5 or the prime number 7. Note that while rehashing, I want to increase the size of my array. That's my aim. So I'm going to take the closest prime number which is going to be greater than 2n. So the closest prime number greater than 6 is going to equal to 7. When n dash is 7, my updated hash value is going to be x mod 7. So now let's see what our bucket array looks like. Zero to n minus 1 or 0 to 6. Now let's apply this hash function to the existing keys. 6 mod 7 is going to equal to 6, so I can add that here. 7 mod 7 is going to equal to 0, so I can add that here. 8 mod 7 is going to equal to 1, so I will add that there. In this way, we have enlarged our bucket array. Now let's see, number of entries is 3, number of buckets is 7. So what have we done? Lambda is equal to 3 by 7. This is definitely less than 1, so it's fine. So by rehashing, we have enlarged the size of our bucket array, made the required change to the hash function, and then applied the new hash function to the existing elements. This is how you perform rehashing.
Okay, so done. Watch. Kelvin?
Yeah.
Not Noel. Okay. So, can understand the rehashing? The rehashing is the process of make the bucket or the hash table bigger. So, how to make it bigger? It is by this formula, 2n. 2n meaning 2 multiply with the size of your hash table. So, and then take the closest and greater prime number to the 2n. So, in this case, your n is 3 because there are 3. The size of the hash table is 3. So, 2n meaning 2 multiply 3. So, 6. And then the next greater prime number to 6 is 7. So we just change the number of table, the size of table here. And then we get, we get the new size of your table. So rehashing is used when there are no null location in your hash table. Okay, so if the system detected that there are no null, then rehashing will be, we can apply the rehashing in your code. Okay, so can understand how the rehashing?
So if no rehash, then if like insert the data into the table, it will cause the endless loop.
Yeah,
Oh,
yeah,
okay.
because it will need to find, because the searching will only stop when it found null. Okay, so can understand lah kan? Load factor we will learn about this in our next slide lah. But if you see here, it is easy to understand lah. Load factor is the ratio of your n entries, the rate of your n entries over your table size or your bucket. So usually if it is full, then the number of entry with the number of your bucket or your hash table is the same. So it will become, if it is full, if your hash table is full, your load factor is 1. So we must avoid our load factor lah. It must be below 1. Your lambda here. Lambda is the load factor lah. So to make sure that we didn't reach lambda 1, and then to make sure that lambda is below 1, we need to make sure the size of hash table bigger than the entries. Okay, so that is the purpose of rehashing. We don't want the load factor become 1, so we need to make sure the size of the table is increased by using rehashing technique. Okay, so we proceed. So if you see the rehash method is in our chapter 10 sample code. So you can explore that later lah. Okay, so we proceed to the separate chaining. It is also known as close addressing, where the close addressing meaning the process no need to search for available entry because we use bucket. Every entry can be allocated to a location directly because, okay, so we don't need to find alternative index or alternative locations because we have, the structure of the hash table is already altered. So it is already, the hash table is, the structure of the hash table is altered, and then so that it can occupy, so it can receive a multiple value. which we called as bucket. So bucket here is different with the bucket from our video previously. In our previous video, the bucket is the table size, the hash table size. But bucket here is also is actually each of the node. We see later lah what is the bucket. So the bucket can be any type of list, sorted list, chain of linked nodes, or array. Excuse me. Okay, so the advantage of separate chaining is we no need to search for empty cells because we can just, if there are any new entry, we can just add it to the bucket. No need to find empty cells. Okay, it is simple and efficient. And then separate chaining may require lesser number of search to find the match. And then it also can reduce the complexity in deletion. And then table size doesn't need to be a prime number. If in the previous technique, it needs to be in prime number, but by using separate chaining, it doesn't need to be in prime number. Okay, so the array or the bucket can be used at location in a hash table instead of linked list. Okay, so here is what we call as bucket. So in each of the location in our hash table, it can containing a bucket. So that bucket maybe can be in type of link, in type of not list, sorted list, chain of linked nodes, or array. So your bucket, this bucket can become the chain of linked node, the list. Okay, so all of that 4 types just now lah. So the hash table, each of the location can containing a bucket. So that bucket is the group of this type of data. Okay, so in this example, this bucket containing a chain of linked node. So each of these is a linked node. So maybe here in this location, there are another bucket. Here is another bucket. So whenever there are new entry, it can just add each of this bucket. It can just add the nodes in the bucket. So there are different types of separate chaining. The first type is the separate chaining. It has duplicate key, and then the bucket also unsorted. So when the duplicate entry is allowed, okay, so maybe there are some setting that will allow either the duplicate entry can allow it or not. But if it is allowed, when there are new entry that has duplicate with the existing chain, then it will be, the new entry will be put here, will be placed here. Okay, so when duplicate search key are allowed, add an entry to the beginning of an unsorted chain. So if there are duplicate keys and then that chain is unsorted chain, you can just put the new entry to the beginning of that chain. Okay, so where new entry is inserted into link bucket when integer search are duplicate and unsorted. So here is the example of duplicate keys and unsorted chain. Another example, another type of separate chaining is distinct keys but unsorted chain. Distinct keys meaning there are no duplicate if each of that keys is unique. Okay, so when you find this type of separate chaining, when there are new entry, the new entry must be added to the end of that unsorted chain. Okay, So the third types of separate chaining is distinct key and sorted chain. So meaning or the change is in sorted way. For example, here it is in increasing, it is sort in increasing way lah, 20, 31 and 44. So when there are new key that is distinct, want to join this chain, then um, the new entry must follow the sorted order of that sorted chain lah. Okay, so it is not at the beginning, it is also not at the end. It must follow the arrangement. Okay, so if it is 37 here, because of 31 is here smaller than 37, and then 45 is larger than 37, so 37 must be keyed in here. Okay, so these are the three types of separate chaining. Okay, so these are the this is the example of separate chaining with the bucket linked list. Okay, so one way to handle collision is to store the collided records in a linked list. Okay, so if all of these entry have the same index, then it can be grouped in a linked list. So all of this entry is actually having collision previously, but we put it in a bucket, and then this type of bucket is linked list. So the array now stores pointer to such list. Okay, so this array is pointing to this list. Okay, so if we want to implement, these are the example of separate chaining in our sample code. So you can find it here in the hash dictionary.java, but under folder separate chaining. So the difference between this separate chaining and then the linear and then the open addressing previously, if the inner class is not table entry. Okay, so um, if we see in our example previously, when we are not using separate chaining, here, it is not here. If previously example in the linear code example, here lah. This is you cannot see. This is the example of hash dictionary that using table entry. So these are the hash dictionary that using node. So why we need to use node? Because we will need to create bucket in your hash dictionary. So that's why it is different from the example that we have learned in linear probing or in open addressing punya example lah. So there are the difference where it is for the separate chaining it is used node. Okay, Okay, so that's why here it says you need to be noted that the inner class of this hash dictionary and the separate chaining is not table entry, because like I said just now lah, separate chaining is we use node, we use bucket, so that's why we need to use the class node. So these are the constructor. So a hash table equal to new node, and then there will be a add, remove, and get value lah. So if you want to explore more, you can find it in here, separate chaining folder. So exercise, but this one I won't ask you. We only apa tu, discuss this lah. Okay, so by using okay, so wait. This exercise is for you to draw the resulting hash table when entry with following sequence keys are inserted to the hash table. Okay, so these are the hash function, and then we use separate chaining as the collision resolution scheme. So we use separate chaining in order to solve the collisions. So these are the hash functions. So when we apply the hash functions, these are the value that we can get. So it says that 12 in the location 7, so there are 12 here, and then after that 44 in the location 5, so 44 here, and then 23, it is in the same location with the first location, so it is stacked up, it is added to the 12. Better guys, I stop the icon first. Excuse me. That icon actually, because it is too freezing, I don't know why I have runny nose because of that coldness. Okay, so when they are new, when they are collision, yeah, I don't know, but it makes me having a runny nose. I need to open. I cannot. Later, I will need to open it again because it will be stuffy here if we didn't open the aircon lah. Okay, so okay, so here by using the separate chaining, we no more need to compute double hashing or quadratic probing because we can just stack it up. So no problem when they are if even though the entry having the same index. Okay, so for example here, 12 and 23 having the same location 7, so it is just added to the bucket. Then 94 and then 37, 39 is having the same location 6. So it is also bucket together. And then for 11, it is in location 5. So it is the same with the 44. That's why it is stacked up. So here, macam it is first come first serve lah. Okay, so it won't check the value of that entry. It just change it. It just arrange it based on first come first serve lah. But it is also depend. But in this case, it is first come first serve. Maybe this is the type of duplicate entry, unsorted chain. Sorry, because it is stacked up at the end. So if you remember, if it is at the end, it is distinct key, unsorted chain. Okay, so our example here is the separate chaining for distinct key but unsorted chain. So that's why it is stacked up at the end. It is added at the end of the bucket. Okay, so the efficiency of hashing. Okay, so we are done with the separate chaining already. So now we will discuss about the efficiency of hashing. So resolving a collision will take time, and then that's why the dictionary operations can be slower than the not big O of one operations. So as the hash table is filled, collision occur more often, and it will decrease the performance of searching even further. Meaning, semakin penuh your hash table, semakin lambat the process, the performance of that you can any operations you need to do to that hash table, either remove ka, add ka. Okay. So since collision resolutions take considerably more time than evaluating the hash functions, so it is the prime contributor to the cost of hashing. So the process of hashing more to the finding solution of collisions rather than evaluating the hash functions. I mean, rather than meaning the process of the time that is used to solve the collisions is the contributor of the time consuming when we are um, doing the hash functions. Okay, so this is what I said previously about the load factor. So to express the cost of hashing, meaning the performance of your hashings, the performance of the hashing process, we define or we measure it using load factor, which is identified by lambda sign. So the load factor lambda is the ratio of size of the dictionary to the size of the hash table. Okay, so this is like the previously lah, the number of entry over the size of the table. So that is the lambda. So what do you think the value of the load factor if the hash table is empty? Who can guess?
Zero.
Yes, correct. Both Noel and Kelvin. It is zero because of course lah, if there are no entry, meaning even though your size of table is 10, then 0 over 10, of course 0 also lah. So the load factor is 0. Okay, so maximum number of lambda. So the maximum value of lambda depends on the type of collision resolutions that you use. Okay, so for open addressing scheme, the lambda's maximum value is 1 when the hash table is full. Meaning, if the number of the entries the same with the number of the size of the table, the value will be 1. For example, your size of table is 10, and then your entry of your dictionary also 10. Then 10 over 10 be equal to 1. For the separate chaining, the number of entry can exceed the size of the hash table. So lambda has no maximum value. Okay, so for open addressing, the maximum value of lambda is 1, meaning the hash table is full already. But for the separate chaining, there are no maximum value for the lambda. Okay, so restricting the size of lambda improves the performance of hashing. Okay, so this is what it means by restricting the size of lambda. Okay, so all open addressing scheme use one location in the hash table per entry in the dictionary. Okay, so for all open addressing itu, if linear, probing, quadratic, double hashing, they are used one location for one entry. Okay, so the dictionary operation, which is the get value, remove, and add, each will require a search of the probe sequence indicated by both the search key and the collision resolution scheme in effect. So all of this operation, get value, remove, and add, will need to go through the process of searching, and then it also need to go through the process of collision resolutions if there are any collisions happen. Okay, so the performance of hashing degrades significantly as the load factor increase. Okay, so meaning the the apa the larger the number of load factor, the performance of hashing will become degrades, will slower. Okay, so it is opposite. The load factor increase, the performance will be degrade or decrease. So to make reasonable efficiency, the hash table should be less than half full. Okay, so we need to keep the load factor or the lambda must be below 0.5, because when the hash table full, it is 1, right? So in order to make sure that the process of get value, remove, add, all of that efficient with a reasonable time, we need to make sure the lambda value is below 0.5. It is must be less than half full. So that is what it means by restricting the size of lambda improves the performance of hashes. Because in this, for the open addressing, we should restrict the lambda size to below 0.5. Okay, so the cost of separate chaining is different. So with separate chaining as the collision resolution strategy, each entry in the hash table can reference a chain of linked nodes. So the number of such change, including empty one, is then the size of the hash table. Okay, so the load factor lambda is the number of dictionary entries divided by the number of change. For example, the average number of dictionary entries per chain. So we take the average of the chain because we have a lot of change, right? And then each of the chain or the bucket is in different size. So how we can get the lambda is we take the average of all of the number of the bucket. Okay, and then we divided it by the number of the chain. So the average performance does not degrade significantly as the load factor lambda increase. Okay, so for the separate chaining, even though the lambda value increase, the performance will not degrade significantly, meaning even though the load factor is increased and the performance actually can be degrade, meaning decrease, it can be become slower but insignificant. The decrease is insignificant, not really can be filled, meaning it is not significant lah. The decrease in the performance is not that can be noticeable. Okay, so that is what it means by does not degrade significantly. So even though that means even though the performance is decreasing, but it is not that significant. Okay, so the restriction for the lambda factor, load factor for separate chaining, as long as it is below 1, meaning as long as it is not full, then it is okay. Okay, so for the reason to maintain the reasonable efficiency for the process of add, remove, we must make sure that lambda, as long as it is not full, even though it is half above half of that hash table, still can be accepted. Okay, so lambda should be below 1 for separate chaining, and so this is the summary lah. For the separate chaining, the lambda value must be below 1. As long as it is below 1, then okay. But for the open addressing, it must be below 0.5. Okay, so if the load factor exceed the bounds, it must rehash the table. So if this, for example, for the open addressing, if the lambda value is more than or equal to 0.5, then rehash must be done. So that is what we do to the we need to do the rehash previously lah. We need to increase the table size. So this rehash can be seen in the method is hash table to full in the hash dictionary. Okay. So far so good.
Okay.
Kelvin?
Yeah.
Okay. So
The
this
Mr. Out of bounds means what?
out the bounds here. Okay, exceed the bounds. The bounds here is referring to this. To this value.
Both of them?
Yeah.
Uh,
But for the separate chaining, the bound must be below 1. But for the open addressing, it must be below 0.5. So the bound here is referring to this value.
if it's at 1 or 0.5, then means need to rehash. Yeah.
If you are using separate chaining and then your load value or load factor is below 1, then
No, it's
you
on,
need to
if it's only 1 at 1. Yeah.
memang 1, meaning
Yeah.
full already lah. Memang of course must do rehash lah.
Okay.
Yeah. Because 1 meaning full already. So there are no more process or there are no more addition or operation that you can do. You only can do the remove lah. But when you want to add new entry, cannot already because full already. So if you are using separate chaining, you need to make sure that your load factor must be below 1. And then if you are using open addressing scheme, you must make sure that the load factor must be below 0.5. If it is exceed this value, meaning memang kena rehashing already.
Okay.
But there are no load factor that is over than 1 lah. Okay, so because there are no dictionary, meaning if it is more than 1, meaning your dictionary entry is larger than the size of table. So it is impossible to happen lah.
Okay.
Okay, so these are the comparison between separate chaining and open addressing. So the advantage of separate chaining compared to open addressing is it can provide faster dictionary operation on average, And then it can also use smaller hash table because we don't need to add, except when the it is full lah, except if the load factor of separate chaining is equal to 1 already lah. Okay, so it also needs less frequent rehashing. Okay, so if both approaches have the same size array for a hash table, separate chaining use more memory due to its link change. Okay, so because when you use a link change, it means that more memory will be used because there are more memory need to be allocated to put to place that link chain. So among open addressing scheme, double hashing is a good choice. It uses fewer comparison than linear probing. So additionally, its probe sequence can reach the entire table, whereas the quadratic probing. So in short, in the open addressing scheme between the three linear, quadratic, and double hashing, memang double hashing is the best lah. So these are the advantage and disadvantage comparison between the open addressing scheme. Okay, so linear probing, because of it is using simpler equation, then it is easier to implement, but it can create cluster in the table, primary cluster. Okay, quadratic probing, it can reduce the primary clustering problem, but because of its formula, it's a little bit complicated compared to the linear probing. It requires more effort to compute the indices for the probe sequence than the linear probing. And the double hashing, it can eliminate the secondary clustering in the most cases. Okay, but the disadvantages, it can be time consuming to compute the two hash function. Okay, so these are the topics that we have learned in this chapter 10, in our last chapter, which is we have learned about how to write the application program that use ADT dictionary in our practical. Okay, so and then you should learn how to override the method hash code for a class whose instances are to be used as a search key. So we can actually override the hash code for any object. It is best for if it is the object class instances, then we can just override it based on the logic that we think is suitable lah for that object. For example, previously we have an object yellow pages, the dictionary that containing all of the number of phone number, and then the suggested of hash code, I mean the process of getting the hash code is we only take the last four number of that phone number. Okay, so that process can actually determined by the programmer themselves, how to determine the hash code, what part or what are the formula. If you want to use any formula to generate the hash code, it is based on the programmer. Okay, so implement hash functions and collision resolution scheme. So we already know that hash functions has two steps, which is first create the hash code. Second is to compress the hash code to become the index, and then the collision resolution schemes where we have learned two, which is open addressing and close addressing, which is the chain, separate chaining. Okay, and then we already discussed the advantage and disadvantage of various hashing and collision resolution scheme. So we know that between linear, quadratic, and double hashing is the best, but separate chaining is better than the open addressing. Okay, so describe clustering and the problem it causes. Okay, so clustering can make the searching or the adding, the operation of adding and searching become longer, because if they are, because when you do adding you need to search by one after another. So if they are a cluster, so you need to finish all of that cluster before you can find the empty or available space. So that's why the clustering can decrease the performance. Okay, so it is now already 11:01 a.m. Do you have any questions?
This
No.
this afternoon got need to demo.
Yes. This afternoon, right? To demo your assignment, right?
Oh,
Yeah.
okay.
Okay, so please prepare lah, huh? Sorry, I
Okay.
forgot to remind you all, but nasib baik.
Need to need to wear formal or just casually can.
Let me check the rubrics first. Either they have marks for attire, but if no, then you can wear any lah. But I will get back to you later lah, and then we'll WhatsApp you if it needs apa
Oh, okay.
wear attire, a formal attire. Okay,
Okay.
I will WhatsApp Noel and you lah, both of you. Okay, so if you don't have any question or if you have any questions, then you can ask in our later class lah. Okay, bye.
Okay. Thanks.
Okay, bye.
Thank you.